Okay, thank you very much for coming to listen to this talk after such a long day and full of events, especially for people who went down to the sea. And I thank especially the organizer for inviting me to give a talk here. It's always a pleasure to speak in this nice lecture hall. And this talk is supposed to be one of the simplest in the conference, and it will describe a computational approach to something. And first of all, I'll give you motivation why it's interesting to study this something. And this is based essentially on two papers. One paper with Morihiko Saito, which is rather old and theoretical, and another paper which is quite recent and is really computational. And so you see, first of all, we'll define the main objects, which are Milnor fibers and monodromy and things related to them. Then we'll describe our computational approach, which is based on some general techniques. And finally, we will give some examples where our approach gives results. So I will fix the simplest interesting case, that is a reduced plane curve in the projective plane. And I will denote by S the polynomial ring. And in principle, one can do everything in this talk for hypersurfaces with isolated singularities in higher dimensional projective spaces. But I will restrict to this case because here the results are simpler to present and more complete. And so we consider the smooth affine surface defined by the equation f equal to 1 in C3, the affine three-dimensional space. This is called the Milnor fiber. And because the polynomial is homogeneous, it comes with a mapping H, which is a monodromy morphism, which is just multiplication by theta. Theta is this d root of unity, or any primitive d root of unity, if you like. And this is called the monodromy of f. And the monodromy induces monodromy operators if we look at the cohomology of the Milnor fiber. And they are defined in this way, so we use the inverse, and this is explained by many reasons. And then we can, these operators you will see soon, they are semi-simple, so essentially they are determined by their eigenvalues, and the eigenvalues are roots of these characteristic polynomials. Okay? And so even at the level of the map H, because we have such a simple formula, the d power is identity. This implies that all the monodromy operators are semi-simple, so the roots are these roots of unity. H0 is very simple, and moreover we have this alternating product, which is completely determined by some easy to compute invariance, the Euler characteristic of the complement. And so essentially, if we want to compute everything, it's enough to compute this polynomial, which is called the Alexander polynomial of the curve. And why we pick delta 1 and not delta 2? Because delta 1 is much smaller in degree than delta 2. So this is why we choose this to be called the Alexander polynomial. And so, first of all, if we consider the case when this curve is smooth, then everything is very simple and completely known, because then f has an isolated singularity at the origin of C3. And John Milnor has studied isolated hypersurface singularities and proved a lot of things about them. In particular, the Milnor fiber is homotopy equivalent to a bouquet of two-dimensional spheres. And this implies, of course, that H1 of f is trivial. And moreover, it's very easy to compute this, because this is just the Euler characteristic of P2 minus the Euler characteristic of the corresponding curve. And this is just 3 minus 2 minus 2g. And you know the formula relating the genus with the degree for a smooth curve. So in the case of a smooth curve, we know pretty well what's going on. So there are some interesting relations between our question and Hodge theory. And H1F, according to Deligne, has a natural mixed Hodge structure. And this mixed Hodge structure admits a direct sum decomposition, where the first term is a fixed space under the monodromy, or the eigenspace of the corresponding to the eigenvalue 1. And here I put the direct sum of the eigenspaces coming from eigenvalues different from 1. Okay, and then it is practically well known that the first part is a pure Hodge structure of type 1,1 and has dimension r minus 1, or r is a number of irreducible components. So this causes no problem. We know everything as soon as we know the number of irreducible components. And this part is a pure Hodge structure of weight 1. And in particular, for lambda different from 1, we have such a decomposition. So the corresponding Hodge decomposition is equivariant. So we can look at the eigenspaces corresponding to lambda in 1, 0 type and in 0, 1 types. And we have this relation by conjugation, because 1, 0 type and 0, 1 correspond by conjugation, and conjugation changes lambda to lambda conjugate. So all of this is very clear. And now maybe some of you are already, maybe half of you are already asleep, because you say, very well, this is nice, but I am not interested in affine algebraic geometry. I'm interested in projective algebraic geometry. So let me explain you that this has something to do with projective surfaces. So I can consider a surface associated to my curve, which was already, this construction was already considered here. So I look at this surface in P3, and of course this is just a ramified covering over P2, and this covering actually is a Galois covering. With group given by the multiplicative group of d roots of unity. And if I define the action of the element theta, which is an element here on a point x, y, z, t in P3 by this formula. This essentially gives me an extension of the action, of the monodromy action on the Milnor fiber, to this singular compactification of the Milnor fiber. This is a singular compactification of the Milnor fiber. And instead of speaking of eigenvalues associated, eigenspaces associated to an eigenvalue, I can look at characters of this dual group, which can be identified to this group. And for each such character, we have the following relations. So the eigenspace of the Milnor fiber corresponding to such a character corresponds to, so the Milnor fiber is smooth but not compact, so to have duality I have to, maybe I have to take dimensions, anyway. To have duality I have to take compact supports and replace the character by its conjugate. And what is interesting is that this guy here becomes the same as the corresponding, the dimension of the corresponding isotypical component of this singular surface. And now if I take a equivariant minimal resolution, it turns out that this H3 does not change. And again, if I'm interested just in dimensions, now I can apply Poincaré duality, and this is the same as the dimension of H1. And so you see, if I am able to construct Milnor fibers with a lot of eigenvalues different from 1, so with big dimensions here, I will be able to construct smooth surfaces with a big H1, and possibly with big and interesting fundamental groups. And so the two questions are naturally related. So, so the main question is, given the curve, let's say by the equation, and this root of unity lambda, determine the multiplicity of this root of this eigenvalue as a root of the Alexander polynomial. That is, determines the dimension of this space. That multiplicity is exactly the dimension of this eigenspace. And a more precise question would be not only to compute the dimension of this space, but to describe a basis, maybe in terms of rational differential forms, for this space or for some Hodge component of this eigenspace. And this might be useful if you have a finite group acting on the Milnor fiber, and if you want to compute the invariant part, if you have an explicit description of the cohomology, then you can do everything you like with this cohomology space.
In this, we've got dimensions there, but if you just take the map from H1 of F into H1 of V tilde, is that an isomorphism on the...
Yeah. Everything is natural.
So that's saying H1 of F, if you will.
Yes. This was a result of Steinbrink long time ago. Okay, so the complete answer is again known if C is smooth. And in fact, for any smooth projective hypersurface by the work of Griffiths and Steinbrink, and maybe I will record the result here. So if pardon?
You say this answer is known in the case of H2, so you mean H1?
Yes. No. The answer is known for H2 because in the case of a smooth curve, H1 is trivial. It's equal to 0, as I explained over there. And so the only group to look at is H2. And for H2, the answer is known. And it goes like that. I look at a quotient of the polynomial ring by the Jacobian ideal. And I call this a Milnor algebra of F. And then this is a graded Artinian ring such that the components are trivial for j bigger than 3d minus 3 times d minus 2. And if I take a monomial if I consider a monomial basis, for this object, then I can associate a family of differential forms by the following formula. This omega is the form you know very well from differential geometry, maybe. And this is nothing else but the contraction by the Euler vector field of the top differential form. Okay? And the statement is that if we choose a basis here, any monomial basis, this will give you a basis for H2. And moreover, because everything is homogeneous, you can see the action of the monodromy on this group, because you can check how it acts on everything. And for instance, H2 of this is just theta minus the degree of this times the class. And so we have a complete description of the action of the monodromy in this case. Okay, now for singular curves, several answers have been given by Hélène Henault, Anatoly Lipgober, Arthur Bartolo, and many others, so I won't review everything. But there are a lot of activity in this area. And in my opinion, the answers are not completely satisfactory because there are still a lot of open questions, very simple open questions, even in the case of line arrangement. So what is a line arrangement? It's just a union of lines. So this means that the polynomial f is a product of linear factors. And here the major question is whether the Alexander polynomial is determined by the combinatorics, and this means by the incidence relation between the lines and the intersection point. So if I have two line arrangements with the same number of lines, They have the same combinatorics. If I can establish a bijections between the lines such that two lines meet in a point, if and only if the corresponding two lines meet in the same, according to the same pattern. And the answer to this question is not known.
That should be known.
I don't know. So, you see, the complete answer is known only in a very special case for line arrangements having only double and triple points. And this is a very recent result, you see, and quite difficult to prove. Actually, Papadima and Suchu proved that this Alexander polynomial has this factor, which is obvious because it's a number of irreducible components minus 1, plus some cubic roots of unity, and the number of cubic roots is at most 2 and is determined by the combinatorics. So you can construct something in a Orlik-Solomon algebra, which is determined by the combinatorics. You take mod 3 version of this algebra, you do some tricks, and you determine this invariant, and this appears in this theorem. But in general, nobody knows, and if you are able to construct such examples, it will be great. People will be happy. Moreover, at a recent conference in the United States, Mike Falk announced that he can prove it in general. And I was not there, but they sent me the slides of his talk. And after the few pages, I discovered a big mistake. So I wrote to him. He told me it's not a serious problem. I will send you next week the corrected version. But that was 2 months ago. So I'm still waiting for the corrected version. Anyway, so this is one example of such a line arrangement. And I will show you some kind of a magic. At least for me. So if m is equal to 2, I can draw this line arrangement in the plane in the following way. So you see that there are four triple points and 3 double points. Okay, and for m bigger than 3, there are m squared triple points and 3 points of multiplicity m, which are this essentially. So this corresponds to a pencil. If I take the first 2 equations and the first 2 factors and consider the pencils determined by these 2 factors, this pencil has these 3 points at the base points. And so my claim is that for m big or equal to 3, you cannot draw the real picture of this. Can you see the reason why? Because there is an old result by Sylvester. Now this is called Sylvester-Garai property, which says that any real arrangement has at least 3 double points. And in this case, there are no double points at all. So this cannot be real line arrangement in the plane. So we cannot draw pictures, and this maybe explains why things are complicated. Okay. So here, until recently, this was an open question, and I will tell you the story along my talk, what is the answer to this. And more generally, there is a strange conjecture by Papadima and Suciu, based on empirical observations. For the moment, the only roots of Alexander polynomials are roots of unity of order 1, 2, 3, and 4, nothing more. And we are not able to construct line arrangements with more complicated eigenvalues. Okay, so now maybe I will start to describe our approach. And so omega j denotes the graded S module of differential j forms with polynomial coefficients on C3. I consider the complex obtained from the usual Durham complex replacing the differential by the wedge product by the differential of f. And this is nothing else but the Koszul complex of the partial derivatives of the polynomial f. And I will fix now an integer till the end of my talk, and this integer will be between 1 and d, and I will denote lambda to be this d roots of unity, okay? And then one has the following results. So, this theorem tells us that there is a spectral sequence starting with E1, and E1 is in principle computable because it's just given by homogeneous components of the cohomology group of the Koszul complex. So the Koszul complex is just an algebraic object. You take cohomology and you look at some homogeneous components. And the limit is exactly what we wanted in some sense, the eigenvalues of the monodromy on the Milnor fibers. But the graded pieces with respect to some decreasing filtration on the Milnor fiber cohomology, and this is called the polar filtration. And moreover, this spectral sequence degenerates at E2 when the curve is nodal. Okay, so why this theorem has two dates so far apart? So actually it was stated in my paper in 1990, and the proof was a little bit naive, and it was reproved from a modern or sophisticated D-module point of view in this paper with Morihiko Saito. Okay? And of course in this paper we have added many new results. Okay? In particular in this paper we prove that it degenerates in the case of a nodal curve. Okay, so I would like to say a few words on this polar filtration. So there are a few important facts. The first fact is that if I look at any cohomology group, this filtration is larger than the Hodge filtration. Maybe I put M because K was fixed. Okay, and if we look at this same statement for the so U will be E2 minus C. I recall you this notation. So if I consider what happens for the eigenvalue 1, because this is just the eigenvalue 1, this is just a result which was proved many years ago in a paper by Delin and myself. I guess again 1990. And somehow it was used by me and other people to obtain information on Alexander polynomial of plane curves, but with a different approach, not with the approach I'm presenting you today. And so the second observation is that even in this very simple setting, the two filtrations are distinct if we look at H2 on U. We have an example in the papers, and an open question. I guess that we have equality on H1 of F. At least in all examples where I have computed this, I have equality, and the claim is okay on the eigenvalue 1, because the Hodge structure of this space is very simple, so we definitely have equality, but maybe we have equality everywhere. Okay.
So, with respect to the sequences, the right-hand side was independent of K. Is that the limit?
This spectral sequence depends on K.
Yeah, but the limit doesn't have K.
The limit depends on K because lambda was defined in terms of K. Yeah. If you remember, lambda was defined in terms of K, so this is why the two are related. Okay, and we have this conjecture that not only for nodal curves, but for any curve with weighted homogeneous singularities, we have degeneration at E2 term. And what is known is that as soon as there is one singularity which is not weighted homogeneous, then one cannot have such degeneration. Okay? And this is how the spectral sequence looks like. And in fact, you should imagine this line as being continued to infinity, and this line to be also continued to the infinity. And we have infinitely many ladders here, but in some sense they are not important in many cases because of this result. At least if I assume that all the singularities are weighted homogeneous, then I can evaluate the dimension of the second order terms in terms of spectral numbers. I will say a few words on what are these spectral numbers. And the idea is that these spectral numbers are always between 0 and 2, strictly contained. And so the top differential in that figure is injective, and all the differentials which are above and which are not drawn are isomorphism, and that's why they are not represented because when I pass to H2, when I take kernels and co-kernels, I get 0. So they do not contribute. And so the corollary is that for such a curve, I have the generation at E3. So E3 is definitely enough. So our machine will not run too long before giving us complete results. Okay, so let's say a few words on these spectral numbers, at least how to compute them in simple cases. So I will assume, I will give you just an example. Assume that I have a local equation of a plane curve singularity of this type, and then I will do the following thing. I will consider a rather strange fraction, which depends on A, and I multiply this with the same strange fraction in terms of B. And this, of course, is a sum of rational powers of T. The exponents here are exactly the spectral numbers of the singularity. So if I have a singular point which in local coordinates has this simple form, for instance, if I have a cusp, A equal to 2, B equal to 3, and this formula defines me exactly what are these spectral numbers. And the general definition involves Hodge structure on the Milnor fiber, and it's a little bit complicated, so I won't give it right now. The important fact is that in simple example, we can really compute this and get estimates on the dimension of second order. Pardon? There is no action of monodromy because I fixed the K. K is fixed. But if I make the direct sum of all, then I can rephrase it in terms of some action. That it's already split into eigenspaces or isotopy types.
Do you have a conjecture in terms of some invariance of singularities about where the spectral sequence should be generated in general?
No, I don't have a conjecture. So I have proved many years ago that for arbitrary hypersurfaces it converges in a finite number of steps, but I don't know after how many steps. And it's an interesting question. Okay, so now we go back to Alexandru polynomials, and you see the spectral sequence is a machine. And the first differential is very, very simple to compute, but not the second one. So the first differential actually, you will see that the elements of the E1 terms are cohomology classes in the Koszul complex, so they are represented by differential forms. And here the first differential is just given by taking the exterior differential of this form. So this is somehow in H2 of K, and this is in H3 KF, and this is D1, very explicit, one can do computation. But for D2, things get really complicated, and so one should try to avoid asking questions about this. And what is a good point is that, so this is a result in the paper with Gabriel Sticlaru, which says that even if the spectral sequence does not degenerate at E2, we can state exactly when lambda is the root of the Alexandru polynomial. So it is a root if and only if either this term or the complementary term, you see k prime is given by this formula, if one of these should be 0. And moreover, we have this evaluation for the multiplicity, and this gives us exact answers if one of these is equal to 0. And you will see at the end an example where this really happens. So if you are lucky, you can compute completely the Alexandru polynomials using this result. And here there is no assumption of weighted homogeneous singularities, and this is good because many interesting curves, I will discuss a little bit later, the free curves in P2, the free curves usually have non-weighted homogeneous singularities. Okay, so now I will explain the algorithm. I define the CGGs just the kernel of this wedge product by df, and these are just the CGGs involving the partial derivative of the polynomial. I call them sometimes Jacobian CGGs. And what is good is that computer software like Singular or Cocoa or other software give you rapidly generators for this S module. So this is not just theory, it works in practice. They gave you generators, and in particular if C is a free curve, which means that this module is actually a free S module, then the software gives you a basis and you can compute precisely all the homogeneous components. Okay? And then you have to compute the kernel of this map. This map corresponds to what I said over there about the first differential, D1, because you see it takes such a form to this class, which is exactly the class in the Milnor algebra of the, if you take the differential of this, it will be this polynomial times the top differential form dx, dy, dz. So essentially this will determine if this is 0 or not. And then I can make some kappa q is the dimension of the kernel of this, and this has to be corrected by the dimension of this space because this, all these are in the kernel of this morphism delta q. They are in the kernel if I look not on the CGGs, but if I divide here with the Koszul type CGGs, and Koszul type CGGs are exactly what comes here. And in the spectral sequence, I have the quotient between the CGGs and this image. And that's why I have to make this difference. Okay. And after all this, I get exactly the dimension of the two terms of the spectral sequence. And moreover, if by chance I get a two-form eta, which satisfy both conditions, that is df wedge eta equal to 0, and eta is a closed form, then it gives rise to an element in the cohomology in a very explicit way, where this denotes a contraction by the Euler fields of the form eta. Okay? And this is a special case of a general result. Consider the modified Joram complex, and modify in the sense that I use a new differential like that. And then one had the following result, which I proved in the case of a homogeneous polynomial alone, and then when f is the Milnor fiber, and then in a paper, my first paper with Morihiko Saito, when f is an arbitrary polynomial and f is now the generic fiber of the polynomial. And this says that we have such an identification between the monodromy of f and the cohomology of this complex. And what is important is that when f is homogeneous, this correspondence, under this correspondence, the homogeneous components here corresponds to monodromy eigenspaces here, exactly as in the case of smooth curves treated by Griffiths and Stimbrick. Okay, so now I come back to the monomial line arrangement, and now you see why I made the Beamer presentation, because I like these horrible formulas. These horrible formulas give you the generators omega 1 and omega 2 for the CGGs in the case of this line arrangement. And this is a free line arrangement, so this is indeed the basis for the CGGs. Okay? And one may ask how to discover such a basis. And the answer is one has to proceed in several steps. First step, I asked my friend Gabriel Sticlaru, who is a computer scientist. He computes the CGGs with singular for several values of m, maybe 10 values, and we look at the results. And after that, we try to guess the formulas. It's easy to check that we have the right formulas because we compute the wedge product by df and we should get 0, right? This is the first step. Second step, we check the degrees. And if I take the degree of this coefficient, which is m plus 1, and the degree of this coefficient, and if I make the sum, and if I get exactly d minus 1, I'm happy, because there is a result saying that if these are not, if omega 2 is not a multiple of omega 1, and if the degrees add up to d minus 1, then they really form a basis. Okay, as soon as I know that the arrangement is free. Okay? And so you see that it's not so difficult to find basis, because a singular or other computer software cannot work with arbitrary m. They will give you just values for certain m's. Okay, and so you see I consider this to omega 1, omega 2, and when m is a multiple of 3m prime, I define an additional omega 1 prime. And why all these are interesting? Because now I can describe basis for this eigenspace. So if I look at this eigenspace for the Milnor fiber of this arrangement, I can tell you exactly which is the basis. The basis is given by this form, which comes from omega 2, when m is not a multiple of 3, and is given by two forms, alpha and beta, which comes from this new form when m is divisible by 3. And in fact, the dimension of these eigenspaces were known before our work. It appeared in a paper by Măcinic, Papadima, and Popescu 2 or 3 years ago. And so they knew the dimensions, but what is new here is that we can produce explicit bases for these eigenspaces. Okay, so now our algorithm allows us to test for many m. So m equal to 25 means that in the arrangement you have 75 lines. 75 lines is a lot of lines. And so for all this arrangement, we have only cubic roots of unity as eigenvalues, right? But in some sense, I do not really trust computers. And so I tried, after writing this paper, I tried to find an independent proof that only cubic roots can occur. And a few days ago, I managed to find such a proof. So now I know that the result is true in general, but the proof goes along different lines, and I will not describe it here. And moreover, for all these values, the spectral sequence degenerates at E2. So we have this conjecture is verified in these examples. So when we set up our algorithm, we hope that maybe we'll discover counterexample to the conjecture, or maybe line arrangement with strange eigenvalues, but for the moment we have not succeeded. Okay, so this is a classical example in algebraic geometry. We have a sextic with 6 cusps on a conic, and everybody knows that it has an Alexander polynomial of this type. And this curve is not free. So this module is complicated, has a minimal set of generators with 1 CCG of degree 5, which is this, and 3 CCGs of degree 7, among which this one. And if you check, both of them verify this. And so according to our general results, they will give cohomology classes. And what is interesting is that they span these 2 cohomology groups. So we have explicit basis for these groups. Before it was known that they are one-dimensional, but now we have explicit basis for them, and this can be useful. And now I will finish with a family of free curves with large Alexander polynomial. So this family of plane curves was discovered by this Spanish mathematician, and they introduced them to give examples of free irreducible curves which are not rational. Because short time ago, maybe 2 years ago, the only examples of irreducible free curves were given by Simis and Pochoniano, and all of them were rational. And so I asked the question, is it true that any free irreducible curve is rational? And the answer is no. And these are a lot of examples giving these examples. And what is interesting about them is that they have large Alexander polynomials, as you see. So this says that the first Betti number of the Milnor fiber is 5m. So we have a lot of space in the cohomology of H1. And according to this philosophy here, we can construct smooth surfaces with large first Betti number, and maybe this will give rise to interesting fundamental groups. This is a question under investigation, so I cannot tell you now the answer. And how to prove such a result? You just put the data into the software, and the software gives you the dimension of these spaces. And you see that in the first case you get vanishing everywhere. In the second case you get vanishing up to half of the dimension, half of the degree, and then equal 1 for the other half. And so our theorem applies very well because we have either 0 or 1, and so the sum is equal to 1, and so we get a precise computation of the Alexander polynomial in this case. Okay, thank you very much.